Hello, my name is Soyeon Park, and I'm here on behalf of my colleagues Dylan Moore and David Sirkin to present What a Driver Wants, User Preferences in Semi-Autonomous Vehicle Decision Making. Let me start by asking you a question. Have you ever been in the passenger seat with a nervous driver and found yourself stomping on an imaginary brake pedal? Well, I have, and I felt very uneasy, and the situation made me somewhat lose confidence in the driver who was actually my friend. What if your own autonomous vehicle put you in the same situation? Here are some scenarios of downtown driving that your vehicle might have to navigate: a pigeon crossing the road, pedestrian entering a crosswalk, stopping at a blinking red light, passing a stopped truck, and people standing by the roadside. How would you want the car to act? Would you want to be informed of its decisions? From now on, I'll be using the industry standard abbreviation AV to mean autonomous vehicles. And we all know that AV technology is advancing rapidly, but a general public perception study published in 2016 found that 44% of people would feel uncomfortable using an AV. Prior literature also shows that driver preference is very important, but we lack an understanding of driving preferences in AV decision making, particularly those involving tactical goals. And tactical goals are short term objectives that require understanding and predicting the local traffic situation, such as maneuvering around a stopped truck. Therefore, we need insights into actions that drivers prefer AVs to take, and whether or not these drivers want to be informed about this action, as these AVs will need to interact with users. Therefore, we designed a study to answer three research questions. First, how do participants' individual differences affect their perceptions of AVs? How do contextual factors contribute to AV decision-making preferences? And how can aligning individual preferences with appropriate contextual factors optimize the perceptions of AV performance? Given the current lack of insight about preferred AV features before wide deployment, we're providing through our work an ontology of real-world situations with AV decision-making scenarios. We're also providing insight as to what driver preferences of participants' desire are for semi-AV decisions, particularly action, and also inform, which can be in the form of alerting. We're also providing design principles for incorporating driver preference in AV decisions, along with an influence diagram that visualizes this within the semi-AV decision-making process, and that is to help guide future autonomous vehicle development. To give you an overview of our study, we first video recorded a drive in downtown San Francisco, California, and chose 18 brief everyday driving scenarios, as you can see on the right. These video clips averaged around 9 seconds in length and were at a maximum of 20 seconds. We also created a survey and contextualized these videos as experiencing a semi-autonomous vehicle drive. And we called it semi-autonomous because the vehicle would not have complete autonomy and may request drivers for consent or handovers. We also recruited 300 participants from Mechanical Turk to garner 100 responses for each scenario. Our survey consisted of three main parts. We first collected baseline measures, and these included what they wanted the vehicle to do in whatever the participants deemed to be a critical event. Then we also asked about their perceptions that they had of AVs before showing any of the scenarios, and these 12 characteristics included how trustworthy or confident the car seemed. Then we showed participants video clips and asked scenario-specific questions after each of these clips, starting off with an open-ended text response. This asked what they noticed in the video to see if their observations matched what the clip showed and was later used to eliminate irrelevant responses. We also asked them what they prefer the vehicle to do, so whether to act autonomously or whether to inform the driver and the vehicle of the situation. And then we also asked them how they perceive the AV with the same 12 characteristics that we asked in the baseline section. And we did this for 6 different scenarios, which were randomized and evenly distributed selections from the 18 total scenarios. And we did this to prevent participant fatigue. Then we asked about demographics, including age, gender, occupation, as well as familiarity with autonomous vehicle systems. Now I'll be showing you a scenario called Run Yellow, which is the AV continuing through a yellow light. Let's take a look. So how did you perceive the AV? Did your perception change from what you initially thought of AVs in general? The following are the 12 characteristics that we asked the participants to evaluate the AVs upon. And these questions were bipolar Likert-style word pairs with 1 to 5, meaning, for example, untrustworthy would be 1 and trustworthy would be 5. And this was to elicit subjective perceptions of each AV driving scenario that participants had just viewed. And in conducting principal component analysis, we found that 8 of these characteristics, namely trustworthy, responsible, sensible, pleasant, knowledgeable, intelligent, friendly, and competent, were grouped as what we call impression, and 2 of them, passive and timid, could be grouped in passivity. And now I will show you analyses using these groupings, impression and passivity, that illustrate the participants' change in perceptions. As you can see from the bottom of the graph on the right, there are 2 AV characteristic groupings that I've just introduced, impression and passivity. And the x-axis shows change in Likert scale ratings, which are basically scenario-specific values subtracted by baseline values across participant responses. And anything on the 0 mark means that there's no change in perception, and anything to the left of the 0 mark would be a decrease in that AV characteristic, and anything to the right would be an increase. These are the changes in perceptions for the Run Yellow case, which we just saw, and we can see that the impressions of the vehicle has increased, whereas passivity of the AV has decreased. And this shows that participants might have viewed the AV as being more aggressive or assertive than what they assumed the AV to be prior to watching the scenario. Plotting all the changes in the impression and passivity for all scenarios, we can see that perceptions varied significantly. Most changes in impressions were positive, as you can see. However, changes in passivity were more varied. Now the next scenario that I'll be showing you is called construction worker. And this one is where the construction workers are entering the roadway from the right side. Alright, so what did you want the vehicle to do in this scenario? There are several ways that an AV could act and inform you in any situation. And we decided to look at these 2 dimensions of act and inform as Billings' work on automation functions and human-centered aviation automation showed how an airplane communicates with a pilot through both acting and informing. There are 3 ways that we looked at inform: not informing at all, as well as informing before and after an event. We conducted a pilot study that showed that informing during an event was not perceived to be much different from informing after an event, and therefore we decided to only include informing after an event. In terms of act, that can be broken down into 3 different categories: having no human input at all, which is to act autonomously, or having some input from the driver, which is receiving consent, or handing over the controls fully to the driver, which would not be acting at all. Populating the 3x3 matrix resulted in 5 possible act and inform combinations. 4 of these that you can see on the bottom right are shown as not applicable, as these were not viable options. For example, let's take the very last cell in the bottom right corner. That corresponds to don't inform, don't act. That would not make sense at all because the vehicle would never hand over controls to the driver without informing first that it would do so. In the same way, all 4 of these are not applicable options. And from the participants' responses to the 5 possible answer choices that I just introduced, we looked at what % of participants desired autonomy versus some form of driver input plotted on the x-axis, and what percent of participants preferred being informed, which is plotted on the y-axis. And you can see here a negative slope forming with all these scenarios plotted on this graph, and this indicates more autonomy correlating with less desire to be informed, and vice versa, which is participants who preferred less autonomy also preferred to be informed more. Here I've highlighted the two scenarios that we've just watched, Run Yellow and Construction Worker. And we see differences even though they had similarities in terms of how impression and passivity changed. Here we see that 20% more participants desired autonomy for the construction worker scenario, and that about 10% more participants desired to be informed of the Run Yellow scenario. We also included critical in this graph, and critical refers to the baseline value collected at the beginning of the survey as to what participants wanted the vehicle to do and what they deemed to be a critical event. Participants almost always wanted to be informed in this critical event, and less than 40% of them preferred autonomy. And in all of our video clips that you just watched, the AV acted autonomously without informing the participants. In other words, this meant that there's act and no inform as a default AV decision for all of our clips. And we investigated the consequences of alignment and misalignment of actual AV decisions with driver preference using this. This chart on the right that I'm showing you is similar to the one that we saw earlier. Instead here, we look at just the AV characteristic grouping of impression as opposed to both impression and passivity. And we look at the changes in impression based on whether the participant preference aligned with the act no inform default. And same as the chart before, to the left shows a decrease in impression, and to the right, an increase in impression. And for the two scenarios that we've watched, we see that when the AV acts and informs as a participant prefers, the impressions remain the same. However, when the driver preference is not aligned with the vehicle's decision, impressions, which consisted of 8 characteristics including the AV being trustworthy, competent, and intelligent, actually decreased. Plotting all these 18 scenarios, we can see that alignment of AV decision with preference led to either no change or positive change in AV perception, except for the two bottommost scenarios, pigeon crossing and pass pedestrian, which were both shown at the beginning of this presentation. And in contrast, misalignment of AV decisions led to more negative impact on AV impression. With the exception of two scenarios, smooth truck and ramp highway, all participant impressions were higher for when the vehicle decision aligned with driver preference than when it did not. From our findings, we developed several principles for designing automated systems. In the first analysis, we found that perceptions varied by scenario. And from this, we distilled the design principle that individual differences will influence mental models of appropriate AV decision making. We next found that preferred AV decisions differed by scenario. And from this, we distilled that drivers may desire handover even in situations where the semi-AV would make appropriate decisions. And lastly, we found that more negative impressions arose from misalignment between driver preference and AV decisions. And from this, we derived the principle that undesirable AV decisions can lead to more harmful consequences, even if the drivers have had positive AV experiences. And in our paper, we also have two more design principles, a few more results, as well as an influence diagram that graphically represents the factors and uncertainties in the AV decision-making process with driver preference incorporated. Given these findings, we anticipate that it'll be important for designers of future AVs to account for driver preferences when developing decision-making algorithms as well as human-vehicle interactions in order to create trusting and satisfying long-term experiences for the drivers. And we hope that our findings and design principles help to start that conversation. Thank you very much.